Thank you so much for the opportunity to speak. I'm Shruti Paranjape. I'm very glad to be here. My first time in Taiwan. So I'm hoping that Yara's talk whet your appetite for a lot of things. Positive geometries, numerators of things in general, and residues at infinity, poles at infinity, these kinds of things, because a lot of these objects, and the ABHY association, a lot of these objects are going to appear in the talk that follows. Okay, so the talk is mainly based on this paper from March with Christoph Bartsch, Taro Brown, Carol Kampf, Umut Oktam, and Yara Trinka. Umut is going to be applying for postdocs, so if that's of interest to you, now you know. And it's also based on work in progress with Callum Jones, who's also in the audience over here. All right, so 3 amplitudes are very friendly objects. We know that they're rational functions. And the nice thing about rational functions is they look like a numerator over a denominator. And locality in quantum field theory tells you a lot about the denominator. It tells you where the poles are, and it tells you what happens near the poles. It tells you that your amplitude factorizes. And so you know something about the numerator as well. You know that every time you're at a singular point, the numerator needs to look a certain way. But how does it look at a regular point, right? So a rational function is fully determined once you know its zeros and its poles. So in this talk, what we're going to be thinking about is the zeros of this rational function. So zeros in physics are reasonably omnipresent, and they're usually associated with some kind of symmetry. So if you look, for example, at maybe the most popular, which is the pion effective field theories, they have vanishing soft limits, which is the Weinberg's soft pion theorem. It comes from the fact that there's some spontaneous symmetry breaking. Okay. So I've given a few other examples here. We'll talk about this in the next slide. There are these stringy zeros that were found by these authors over here. And of course, the zeros that Yara mentioned in his talk just now in the n equals 8 supergravity MHV amplitude. So the set of zeros that I will be talking about today were dubbed hidden zeros. Hopefully by the end of the talk, they will become unhidden to everyone in the audience, and we can start calling them apparent zeros with the amplitude. I'll introduce what they are, and I will hopefully convince you that the existence of these zeros and behavior of the amplitude near them is very intimately related to the good large Z behavior of these amplitudes under some shift. Okay. So the reason I wanted to point out these two in particular is because this meeting is called QCD meets gravity, and QCD has pions and it has quarks. So pions have zeros, an Adler zero, and quarks actually exhibit this, what is called a radiation zero. So when you go quark-quark to diboson, you actually can see over here that there's a dip in the cross section at some angle. And in some sense, these hidden zeros that I'll talk about are a d-dimensional n multiplicity generalization of exactly this radiation zero. Okay, good. So what are these zeros? So these are zeros that are present in this theories like the NLSM, Yang-Mills, and trace phi cubed. And recently, they were discussed in a lot of detail in this paper over here. Good. So at 4 point, this looks very simple. It's just an angle zero. So when T or S13, some Mandelstam goes to 0, the amplitude vanishes. At 5 point, again, it looks like S13, S14, set those to 0, your amplitude vanishes. At 6 point, you have two options. You can either do this set of 3 Mandelstams or this set of 4 Mandelstams. So this is just some kinematic point at which the amplitude vanishes, and systematically for all n, you can predict where these points occur. I will just point out that the first type of zero, meaning when I set all but two of the S1I Mandelstams to 0, that looks a lot like an Adler zero. It looks a lot like a soft limit, but it's one step away. And because we're in d dimensions, we can always be one step away from the Adler zero. Okay. So trace phi cubed is the most friendly theory I can think of where you can see these zeros. So this is the trace phi cubed amplitude for the ordering 1, 2, 3, 4. And you can see when I add the two contributions up, there's a numerator. The numerator is exactly S13, so sending it to 0 gives you 0. And if you speak associahedron, then the reason this occurs is because you can write the associahedron, for example, the 5-point associahedron, in terms of these Minkowski sums. And every time you hit a Minkowski sum component that is one dimension lower, you get a 0. So you can actually read off the presence of zeros just from this equation over here. This is only true for trace phi cubed. It's not true for the nonlinear sigma model. It's not true for Yang-Mills. And so what I want to do is give you an explanation, a symmetry explanation as to why zeros exist in these other theories. So to do this, I'm going to introduce this bookkeeping device called the kinematic mesh. You don't have to take it more seriously than a bookkeeping device to take care of your kinematics. So these are the x variables that Yaroslav introduced in the ABHY associahedron in the last talk. They're planar variables at which planar amplitudes have poles, right? And I draw this triangular mesh region. Yeah, I draw this triangular mesh region, and the vertices now have the x variables on them, and the plaquettes, or these little diamonds, have the S or Mandelstam variables. So the difference, the distinction I want to make is where I will encounter a pole and where I won't encounter a pole. So the plaquettes contain kinematic invariance, so S Mandelstam invariance, where I won't have a pole, and the vertices have Mandelstam invariance where I will have a pole in a planar amplitude. Okay. Good. So I think Song will also say more about this in his talk later, because there's a lot of rich surfaceology that goes behind all of this discussion that I'm not going to discuss here. Okay. So now, once I have this mesh, any rectangular region that I can draw in the mesh is a 0. Okay. So I can draw this rectangle, or this rectangle, that rectangle, and every rectangle I draw, I just set all of the Mandelstam invariants associated to that rectangle to 0, and the amplitude vanishes. Okay. Good. There's one more time. So what I like the most about these zeros is that when you go near them, despite the fact that it's a regular point, the amplitude factorizes. So this is not something that locality asks for. It's something that just happens to be true for these amplitudes in NLSM, Yang-Mills, and trace phi cubed. So what does the splitting look like? I choose one of the zeros, which is this rectangle over here. I then choose one of the components to be non-zero. So this is how I'm, in this sense, I'm near the 0. And you can see that the mesh automatically splits into two triangles, this orange one over here and the pink one over here. And it turns out the amplitude also splits into an orange 7-point amplitude and this pink 5-point amplitude, with an important prefactor that we will return to later. But all of this can just be read off the mesh, and it's very unclear what physical principle tells you that this should happen. So all of that was about the scalar theories, but I've been saying Yang-Mills, so obviously there must be some spinning version of this. And the spinning version is whenever the mesh tells you that Sij is 0, I set all kinematic invariants or Lorentz invariants that I can build from epsilon I, pi, epsilon j, and pj to 0. So this condition is what sets Yang-Mills amplitudes to 0. This is how it goes to 0. The contact term goes to 0, and then the pole terms go to 0. All right, good. So now let's come to what I want to talk about in this talk, which is I would like to show you that the existence of these zeros is due to a symmetry. It's due to color kinematics duality. I would then like to talk about how one should understand the splitting near these 0 points, and that the splitting near the 0 points is related to the fact that all of these amplitudes have some well-defined large Z behavior. And then finally, I want to shove these through the meat grinder of KLT and then show you that both of these properties also are shared by uncolored theories in a way that the kinematic mesh could never have shown you. Okay, so let me pause really quick to see if there are any questions about the basics of what a hidden zero is or what splitting is. Okay, excellent. So let's do part 1. Good. So these are the theories in which hidden zeros were first shown, and anyone who looks at this list of theories will immediately notice that these are all related to the double copy. In particular, they're all related to single copies. The only reason I say related is because the first example is not actually BCJ compatible, but its cousin, biojoint scalar theory, is definitely BCJ compatible. So these are all single copy theories. What do I mean by single copy? Well, JJ gave a nice talk yesterday about the double copy. We will be thinking about it slightly differently. We'll be thinking about it from the KLT point of view. But the idea is the same. There's some web of theories that are connected by these multiplicative relations. And the KLT relation tells you, for example, that in Born-Infeld, the 4-point amplitude looks like some kinematic kernel times the Yang-Mills amplitude times an NLSM amplitude. Good. So the amplitudes that go into the double copy is what I'm going to call a single copy theory. This is a double copy theory. And then trace phi cubed is related to bijoint in this way. It's diagonal. Okay. So this is the BCJ relation at 6-point. And it's really a trivial observation. You now go on to the 0. And that's the 0. You can see that each of the prefactors actually vanishes on this kinematics, right? So what this means is as long as none of the amplitudes on the right-hand side have 2 particle poles at these locations, the amplitude on the left-hand side will have to vanish, meaning the BCJ relation tells you that you have to have a 0. You can do this for the other 0 as well, and this continues to happen. For trace phi cubed, I just write down the same BCJ relation. On this side, it's a trace phi cubed. On this side, it's biojoint scalar amplitudes. But the same thing holds. The prefactors will tell you that you have to have a 0. Okay, so what is happening to these 2 particle poles? What is happening is that in the nonlinear sigma model, there are no 2 particle poles, so you're safe. In trace phi cubed, none of these amplitudes, because of the orderings, none of these have poles at the locations which would be problematic. For Yang-Mills, we know 2 poles exist naturally, but the 3-point amplitude actually vanishes on the support of the polarization conditions. So all of these single copy theories, including df squared and f cubed, with higher derivative corrections, as long as you satisfy the BCJ relations, you have a 0. And an important part of our paper from March was that we showed that this is true for all n and for any type of 0. But this slide is busy, so this is the takeaway. The takeaway is that it works at n point. Good. Good. So now in the second part of the talk, I would like to talk about the splitting. So we saw that being color kinematic dual guarantees that these hidden zeros exist. Where I want to now go is that that also implies that splitting must happen near these zeros. Good. So this is the 6-point amplitude. This is the near zero condition, or one of the near zero conditions that you could choose for the 6-point amplitude. And this is the splitting relation that you can write down. Now, one thing you'll notice about this is that the factor that sits in front looks like 1 over x plus 1 over x, which means it looks like the sum of two residues at x14 and x36. And if you don't speak x, this is S123 and S345. Okay? So these are just some Mandelstams, some poles. And what I would like to do is show, is basically get to this splitting relation from a Cauchy theorem style argument. So I want to introduce a shift of my x variables that allows me to access these residues and obviously this one as well. Good. Yeah, I don't think I need to sell recursion relations to this audience, so but in case you want to be sold on it, you can pay attention for the next few slides. Good. So we want to use Cauchy's theorem, and for that we introduce this shift over here of x14 and x36, which are precisely the two x's that show up in our splitting relation. Now the x's are fully consistent. They already solve momentum conservation, so I don't have to do anything more in principle. But I do want to do something more because I want to make sure that I am on this near zero kinematics. So to do that, I solve for all of the other x's such that this pink diamond over here of c's is 0, meaning that I am actually on the near zero kinematics. Once I solve for that fact at 6-point, for example, I get these two x's, x15 and x26, to be shifted. Okay, so this gives me locations of poles at other locations, which I'm going to call Zij, which is when an Xij it goes to 0. So this is in addition to the ones that I wanted to shift in the first line. Okay, good. So now I can do the usual thing. I contour integral, I put the contour around 0. I use Cauchy's theorem to pick up residues everywhere. And what I'm hoping is that that then gives me the splitting relation. So where are the residues of this integrand? So the first one is, of course, at z equals 0. I put that in artificially by hand. And an at 0 is exactly the amplitude on split kinematics. Okay. The other two locations are what I'm hoping gives you the splitting relation, which is when z is minus x13 or x46. Third ingredient is what I've been saying one needs to think about much more carefully, which is the fact that at z equals infinity, the residue actually vanishes. So there is no residue at infinity. This allows me to close my contour for Cauchy's theorem. And then these other Zij's, which come from these kinds of poles. So the 6-point amplitude, for example, at x26 goes to 0. It's just a regular pole. Locality tells you have factorization, and it looks like this. And these particles in pink over here are telling you that this is actually a 0 of the lower point amplitude. So this is your main recursive step. The fact that whatever you landed on is actually vanishing because of lower point amplitudes having these 0 conditions. And you can see that directly from the mesh. Actually, you can choose a point that you want to factorize at, and you will see that no matter where I put this blue point, there's always going to be one sub-amplitude either on the right or the left that is evaluated on 0 kinematics. All that to say that when I look at Cauchy's theorem, I have this residue at 0, this residue at x13, x46, infinity, but nothing else. Right? And this stuff in pink over here is what gives me the splitting theorem. So what this means is that if I assume lower point zeros and that the residue at infinity vanishes, or good large Z behavior, that is the same as saying I am going to split near zeros. So the logical flow here is that BCJ tells you hidden zeros exist, and then hidden zeros tell you that splitting must exist as long as the residue at infinity vanishes. And for any check that we have done, for any of the amplitudes we've looked at, the residue indeed does vanish. And I think a first principles explanation as to why this happens is still evades us, but hopefully will be in our paper in the next few months. Good. Okay. I think especially for the NLSM, this is surprising because it doesn't normally have. If you just do a random multi-line shift, the NLSM doesn't have good large Z scaling. There's also something interesting that can be said about the object at infinity. This is something I'm thinking about with Max Pradlin, Anastasia Volovich, and their extremely wonderful student, Marcos Skofronik. I'm happy to talk more about this to anyone who's interested. Okay, so in the last few minutes, let's try and put all of these facts through the KLT relation so that we can say something about uncolored theories. And as Yaroslav already motivated for you, uncolored theories are a part of theory space where positive geometries have not been able to go. Right? So a lot of these surfaceology techniques, maybe Julia will have more to say about this in the afternoon, but a lot of these surfaceology techniques, at least as they now appear in the literature, cannot be extended or don't naturally extend to theories without color. And given that these hidden zeros and the splitting are products of surfaceology, it's very surprising that uncolored theories would have these properties. But let's see how it works. So this is the KLT relation at 5-point. And it's the tamest KLT kernel. It just looks like this in this basis. And again, I do what I did with the BCJ relations. I just evaluate on a zero. And it turns out each of these elements vanish. I don't even have to use the fact that the amplitudes vanish. The KLT kernel itself vanishes on this kinematics. If I choose a different zero, it doesn't vanish, which is all to say that choosing the right KLT basis is very important. Another way of saying that is that the KLT formula is basis independent. Another way of saying that is that the single copy amplitudes are BCJ compatible. They satisfy the BCJ relations. Okay. So all of this guarantees that any product of the KLT relation must actually vanish on the support of these zero kinematics. Again, in our paper from March, we showed explicitly that for any n and any zero, any product of KLT with some caveat about the two particle poles again has to vanish on the support of zeros, meaning it has hidden zeros. Now, the two particle poles, let me comment a little bit about them. Again, the NLSM has none, so the special Galilean just inherits zeros. Born-Infeld inherits zeros. Gravity or dilettante gravity, which comes out of the double copy, also inherits zeros as long as you're careful that your polarization tensor actually satisfies the polarization conditions. And then this is also true of other products of the double copy. Okay. Let me briefly now say something about splitting. So the way that we got to splitting in the single copy theories was by saying that our X shift only picked up a certain set of residues. And because we solved for our other X's in a particular way that never shifted any of the individual plaquettes or none of the individual C's, when I look at an uncolored theory, I'm not actually picking up any extra poles. I'm still only picking up these ordered planar poles. And this allows me to write down exactly the same residue theorem and exactly the same splitting relation for these uncolored theories. Now, you should feel uncomfortable because the way I've written this looks like it really matters that it's 1, 2, 3, 4, 5, 6, right? But interestingly, because the mesh is split up into these two regions, you get these uncolored blobs of 1, 2, 3, 4, and 3, 4, 5, 6. So it doesn't actually matter that this is an uncolored theory. Okay. Now, like the last point I wanted to make is that like large Z behavior for a BCFW shift, this large Z behavior under these newer shifts also play very well with KLT in the sense that the KLT kernel itself doesn't shift, which means that if I put in products that have good large Z behavior, whatever I get out will also have good large Z behavior. Now, this allows me then to say that any double copy product must have good large Z behavior, and that means it has to have splitting in zeros. Okay. So I just want to summarize because I think I'm mostly out of time. We now have this very coherent connection between BCJ relations, KLT relations, hidden zeros, residues at infinity, and splitting near these zeros. I think these are all connected in exactly the way that I had in this slide and the corresponding BCJ slide. But there are a lot of open questions still. The one that I'm currently thinking about a lot is there a polytope that resides at infinity that tells you what are you getting when I take an infinite limit? What is this function? Does it mean anything? And does it tell me that the residue actually vanishes? A full set of theories that actually have residues at infinity that vanish would be interesting. A first principles understanding of why these residues vanish is also, I think, an interesting question. And then these, of course, are related to the last thing that Yara talked about, which is there some geometric origin for these uncolored theories having hidden zeros or splitting relations? So with that, let me thank you for your attention.
Thank you very much. Time for a few questions.
Hi, thanks for the very nice talk. Just a quick question on the asymptotic, the large C behavior. So for the theories like nonlinear sigma model or special Galilean, do you think this is just like a consequence of their enhanced sublimits, or is it something new?
Good. So I want to emphasize that we're not actually doing any subtractions in this contour integral. So we're not saying, I mean, normally when you use the enhanced soft limit argument, you have something in the denominator over here that you're adding that takes care of the enhanced soft limit. But here it's just 1 over z.
So it's just some new behavior.
It's just some new behavior that I think we should try and understand. It's related a little bit to something called the C expansion. So the fact that the NLSM has a C expansion will allow you to then say that it's residue at infinity vanishes.
Thank you.
Okay. One more question is over there.
Thank you for the nice talk. Just a slightly dumb question. How can we use this condition to bootstrap the tree-level amplitude or constrain the amplitude?
So thanks for the question. So when you say bootstrap, do you mean like in a recursive way constructed, or like just how are these constraints related to one another?
Yeah, it can be both. Like recursively use this zero infinity. How to do it?
Yeah. So the first question I don't know the answer to. I don't know if you can use it to recursively construct the amplitude at any point. But the second question we studied in detail in our paper in March, and it seems like BCJ is the strongest constraint, and then all of that implies hidden zeros, but you can have hidden zeros without BCJ, and you can have Adler zeros without hidden zeros. So there's some like hierarchy of how constraining these conditions are. And it goes, BCJ is the most constraining, followed by hidden zeros, followed by Adler zeros, for example, in NLSM.
Yeah. Thank you.
So maybe I end it here because we're a little bit over time, but we still want to take the full half an hour coffee break, so we're just going to come back a little bit later for the next session. But let's thank the meeting.